Today we will be going through the June 2023 paper 1 physical sciences exam. Without further ado, let's get right into it. So as we all know, question 1 is multiple choice. Therefore, I'll just write out 1.2, 1.3, 1.4, 1.5, 1.6, 1.8, 1.9, 1.10. All right, for our multiple choice questions, we have variable options, which are provided as possible answers, and each question has only one correct answer. All right. So the first one. Which of the following quantities is a tendency of an object to resist a change to its state of motion? We know that is A, that is the momentum. B, 1.2, a ball is dropped from rest at a height above a concrete floor. So our ball is dropped at whatever speed, right? And our speed is also downwards, meaning it's positive, okay? Because look at our graph. Our graph has a positive gradient going up, meaning it's increasing. It's a positive velocity. It's above the zero line, okay? So our downwards velocity is chosen as positive. Now, the ball strikes the floor and bounces vertically up and down on the same spot on the floor. The velocity time graph for the bouncing ball is shown below with points P, Q, R, and S representing different times during the motion, okay? Ignore the effect of air resistance. At which time does the ball reach its maximum height after the first upward bounce? So our ball comes down and it reaches the concrete floor, okay? After it reaches the concrete floor, it bounces up again on the same spot, okay? The fact that I've drawn this in on different spots means nothing. It's on the same spot, okay? Meaning all the momentum, okay, no. It's bouncing on the same spot, okay? It bounces up. It reaches a spot above the floor. It bounces back down. It reaches a spot on the floor and it bounces back up. Now, analyzing our graph, we have the first part of the motion, which grows linearly with time, which represents this motion down here. Then the ball bounces up. The ball bounces up when the moment between when the ball bounces up and it goes back up again, this moment right here up to here will be given by this piece right there. That is the motion, okay? That is the motion, because remember, as the ball is bouncing up, the velocity is negative because we have chosen downwards as positive, okay? So meaning V up is negative, okay? When we get to the top of our motion, the ball then reaches the maximum height and then drops back down, which means V down is positive again, okay? Wonderful. Now, we are asked, what time does the ball reach its maximum height after the first upward bounce? Now, remember that the maximum height is reached when the velocity is equal to 0, and the velocity is equal to 0 at 2 points. The velocity is equal to 0 at point Q, and the velocity is equal to 0 at point S, okay? Now, we are looking for the time at which the ball reaches its maximum height after the first upward bounce, okay? So that tells you that the first upward bounce occurred at this point, right? And then it bounced up and reached maximum height, velocity equals to 0, and then went back down. Okay, let me use a different color for that. It went up, it went down, it bounced, the ball went up, it reached maximum height, and then the ball went down again. Okay, so meaning our answer for question 1.2 will be that should be B. Okay, let's look at 1.3. 1.3, two blocks P and Q of masses M1 and M2 respectively are held at rest on a frictionless horizontal floor with a compressed metal spring between them as shown below. Okay, so from now on I'm just gonna circle in. I'm just gonna use the green pencil to circle in whatever is the right answer, instead of scrolling back up and writing back there again. So meaning for 1.1 the answer is A. For 1.2 the answer is B. So 1.3, two blocks M1, M2, frictionless horizontal floor and compressed spring between them. When the blocks are released and the spring drops to the floor, okay, block Q moves to the right with velocity v. So Q moves to the right with velocity v. Okay, which one of the following represents the momentum of block P after the blocks are released? Okay, that's 1.3. Now for 1.3, we are looking for the momentum of the block P after the blocks are released. Okay, now, well, when the blocks are released, they are released from rest. Okay, they are released from rest. Now, since they are released from rest, it means that momentum conservation tells you that m1v1 plus m2v2 initial is equals to m1v1 final plus m2v2 final. Okay, and we know that both our boxes were held on a frictionless are held at rest, so meaning the initial velocities are 0, which tells you that m1 v1 final is equals to negative m2 v2 final. Okay, so now this question is asking you which one of the following represents the momentum of block P after the blocks are released. Okay, the momentum of block P after the blocks are released. So since the momentum of block 1, the final momentum of block 1 is equal to the final momentum of block 2, right? We may thus the final momentum of block 1 is equals to minus the final momentum of block 2. It tells you that if block 1 is going to move to the right, block 2 is going to move to the left. Therefore, your final answer will be D, m2v to the left. Okay, m2v to the left, because the momentum of block P, which is object 1, is equals to minus m2v final, which is equals to the mass of block Q multiplied by v, which is m2v right there. I hope that makes sense. Okay, 1.4, the magnitude of the gravitational force that spheres x and y exert on each other is F. The mass of x is now doubled while the mass of y and the distance between the centers of the spheres remain the same. Which one of the following is correct for the magnitude of the forces the spheres now exert on each other? Remember Newton's second law, which tells you that the magnitude of the force is inversely proportional to No. The mass of the object is inversely proportional to the magnitude of the force. Yes, yes. So if we are doubling the mass of sphere X, it means that the force that sphere, if we are doubling the mass of sphere X, okay, it means that the force on X is going to be halved, okay? So if the force on X is going to be halved, that means the option we are left with is D. Okay? The force that we are left with is D, because the force that Y feels is due to X, right? And the force that X feels is due to Y, right? Therefore, if the mass of X doubles, if the mass of X doubles, it means the force felt by X is halved, right? But if the mass is halved, right, it means that, remember, the mass of sphere Y is in this case halved, right? And that means the force then doubles. That means our answer is thus, oh, supposed to use a green color for that, D. Okay. Sorry about that. 1.5. A hot air balloon is moving vertically downwards at constant speed. Assume the mass of the hot air balloon remains constant. Which of the following physical quantities associated with the hot air balloon changes during its motion? Is it its weight? Is it the momentum? Is the kinetic energy? Or is it the potential energy? Now, you might be tempted to say it is the weight because the weight is dependent on the height. Well, if you want to say it's the momentum, it can't be the momentum because the velocity and the speed remain the same. Okay, so if the velocity and the speed remain the same, then that essentially means that there is no change in momentum. Okay, the kinetic energy again is not dependent on the height. The kinetic energy is half mv squared, right? Which then tells you that the change in kinetic energy is equal to 0. Why? Because the change in v is 0. We are moving at a constant speed. Now, the last one is thus potential energy, which is also equal to mgh. So which one? Now, we have to consider the fact that the weight is not a physical quantity, okay? While mass given in kilograms is a physical quantity, the weight is a product of the mass and the gravitational force. I'm sorry, I wrote that as mgh, but the weight is just mg is equals to the mass times the gravitational force. The weight is not dependent on the height. It is a physical quantity though. It is not dependent on height. Therefore, your only option that you are left with is D, the potential energy. Because remember, we are moving vertically downwards, meaning there is a change in the height because you are moving from one point up higher to one point that is lower in terms of altitude. 1.6. A learner standing at a roadside records the frequency of sound waves produced by a siren of an ambulance. The ambulance is moving. Okay, so the first thing, a learner is standing at the roadside, meaning their velocity is 0. Records the frequency of sound waves produced by the siren of an ambulance. The ambulance is moving at a constant velocity along a straight horizontal road. Constant velocity along a straight horizontal road. Okay? Thus, The frequency time graph of the detected sound is shown below. Which one of the following statements concerning the motion of the ambulance is correct? The ambulance is approaching the learner and passing the learner. Does the ambulance move away from the learner, then turn and then approach the learner? Does the ambulance approach the learner, turn and then move away from the learner? Or does the learner move away from the learner? Does the ambulance move away from the learner and then stop? So here, this is a Doppler effect question, okay? And your answer is going to be either B or D. Okay, let's look at the first case. If the ambulance is moving away from the learner, right, it means that the frequency that is heard by the learner is going to be less. Okay, now if the ambulance is going to turn, the frequency is also going to change. The frequency observed by the learner is also going to change. So that is what we experience here. And now because it's approaching the learner, the frequency then becomes higher, because the ambulance is what? It's approaching the learner. Remember that for Doppler effect, if the source is moving away from the observer, the frequency is lower. Okay, because think about it. If you're looking at a siren, if you're trying to hear a siren, as it moves away, the sound that you hear gets lower and lower. The volume of it gets lower and lower. So think about that as the frequency. So if the source is moving away from you, then the frequency gets lower. If the source is moving towards you, the frequency gets higher. If a car that is blasting its horn is moving towards you, it gets louder the closer it gets to you. Therefore, B is a possible solution. Now, D. Why is D also a solution to this question? Well, D is a solution because A, we've already explained why it has a lower frequency as it's moving away. Okay, we've already explained that. We know that as the source is moving away, the frequency is lower. This part is lower than this part. This part is a bit higher. Okay, so we've already explained the moves away part. Now, here's the thing. If the ambulance then stops, okay, there's going to be a change in frequency. Okay, there's going to be a change in frequency, which is what we see right here. Okay, now after stopping, the ambulance doesn't move anymore, which explains why the graph then becomes constant, because the frequency that is observed by this learner is then constant because the ambulance is no longer moving towards or away from him or her. Okay, so that is why D is also a viable option. So your answer is either B or D. Moving on. Either one, by the way, either one of these is correct. Either one of these, if you choose either one of these, you will be fine. 1.7. Okay. Two identically charged spheres X and Y carry charges of +2 and -6 respectively. Okay. X experiences an electrostatic force F to the right when the distance between their center is R. Okay, so their electrostatic force is in the right direction. Okay, so the spheres are brought into contact and then return to their original positions. Which one of the following represents the magnitude of the electrostatic force that sphere X experiences now? This is going to be B. Next question, 1.8. In the circuit diagram below, R1 and R1, R2 and R3 are identical resistors. The battery has negligible internal resistance. The power dissipated by R1 is P. Which one of the following is the power dissipated by R2? If now looking at the circuit, R1 is connected in series to both R2 and R3. It's connected in series to R2 and R3. Now, in terms of power, power is the same as potential. Okay. Now, if R1 is using up power P, then the power that is moving through R1 is P, and the power that comes to this point of the circuit is P. Okay. Now, because the power is halved in a parallel circuit, it makes sense then for the power flowing or the power dissipated by R2 to then be 1 over 2P. Okay. Wonderful. Sorry, please disregard that. It's 1 over 4P. It's 1 over 4P. Okay, because if P is moving through here, then P over 2 is moving through this whole circuit, okay? And if P over 2 is moving through this whole connection right here, then when it comes here, it separates more into 1 over 4 and 1 over 4. I hope that makes sense. 1.9, simplified diagram below is a DC motor. Diagrams indicate some changes made to the motor above. Which of the changes to the motor above will change the original direction of the rotation of the coil? Now, in this scenario, the changes to the motor, right? If your coil was moving this way here, right? If you change the configuration, then that means your coil is going to move the other way around. So this change is going to change the direction of the rotation of the coil, okay? If you change the poles. Now, 2 also works because you are not only you are changing the polarity or the polarity of the terminals, right? So that also works. Now, if you look at number 3, however, you have changed the magnets themselves. The south magnet is no longer on the right, but it's now on the left, and the north magnet is now on the right. But however, the south magnet is still paired with your negative terminal, and your north magnet is still paired with your positive terminal. So that means you are effectively not going to change the direction of rotation. It's just going to look like it, but effectively the direction of rotation is not going to change. So meaning your answer is going to be A. And finally, for question 1, an atom has a ground state energy of X. When the atom moves to a higher energy state Y, a line spectrum is observed. Okay, which one of the following combinations is correct for the energy change of the atom and the type of line spectrum observed during the transition? So an atom has a ground state energy of X. Okay, when the atom moves to a higher energy state Y, so you have the ground state, which is X, you have a higher energy state Y, and the distance between them is Y minus X. Okay, so which one of the following combinations is correct for the energy change of the atom and the type of line spectrum observed during the transition? Okay, so if our atom moves from the ground state up onto the excited state Y, okay, we can characterize that as Y to X. y minus x, right? The energy change is going to be, if a particle moves from ground state up to a second energy level, okay, the energy change is going to be given by y minus x, okay? Now, when an atom is moving, when an atom is moving from a lower energy state to a higher energy state, it usually means that this atom has gained energy, right? So if it's gained energy, it means that it's absorbed and it has absorbed some energy, okay? So this would then be absorption. Absorption is a variable, okay? And we also know that if a particle moves from an excited state to ground state, okay, here the change in energy is characterized by an emission, okay? So the emission occurs because in moving from an excited state to a lower state or to the ground state, the atom is essentially losing energy. It's emitting some of the energy that it had in order for it to fall back down to ground state, okay? So in this case, D is correct. We can now move on to the fun questions. Question 2. A block of mass M, okay, is connected to block B, 7.5 kilograms, light inextensible rope. Okay, block B is initially held at a height of that, above the ground, while block A is initially stationary and on the ground. Okay, when block B is released, it moves vertically downwards and strikes the ground with that velocity. Ignore friction. 2.1. Show by means of a calculation that the magnitude of the acceleration of block B was 3.88 meters per second squared while the block was moving vertically downwards, okay? Now, for this question, the first thing we're going to start off with is we're going to start off with the formula. Now, you can choose either to have your velocity upwards as positive or your velocity upwards as negative, and you can also choose to have your velocity downwards as positive or negative. So in this case, we have chosen downwards. We are choosing v down as positive, meaning the velocity of vb while it's going down is positive, okay? Wonderful. So in choosing downwards as positive, we can write an equation of motion to start solving this. We are looking for the acceleration, and we know the velocities. Do we know the time? Do we know the time? No, we don't know the time. So meaning we can use vf squared is equals to vi squared plus 2a delta y. Okay, so from here we know the final velocity of block B. The final velocity of block B is 3.41 meters per second squared. Okay, and the initial velocity of block B is 0 because it was initially held. It was held stationary. The initial velocity was 0. Okay, squared plus 2a into 1.5. Remember, we have chosen downwards as positive, and the direction in which B is moving is downwards. That's the 1.5 is downwards, okay? This tells you that after all the algebra is down, the acceleration is equals to 3.41 squared divided by 2 into 1.5, and that will be equals 3.88 meters per second squared. 2.2. Draw a labeled free body diagram showing all the forces acting on block B immediately after it was released. the forces acting on block B. Now, block B has a light inextensible string attached to it, right? So meaning obviously the first force that is acting on it is T, which is acting upwards. Now, but block B is also moving downwards, is it not? So since it's moving downwards, it means the force of gravity must also be acting on it, because A, it's moving downwards, B, it's not on the ground, so the normal force isn't there to counter the force of gravity. So what do then? We include the force of gravity, or the force due to gravity. And that will be your 2 marks for the labeled free body diagram. This can be written as Fg, weight, force of weight, or whatever you want to write it as, essentially. 2.3. State Newton's second law in motion. Okay, so this one, they look for keywords or key phrases. Okay, so if these keywords or key phrases are omitted, then you lose a mark. The first key phrase is acceleration. That is directly proportional to the force. This is the first one. And now the second compulsory statement or phrase or key phrase or key statement is inversely proportional to the mass of the object. So how would you tie in these two key phrases together? What you would then say is, when a resultant force acts on an object, or when a net force acts on an object, the object will accelerate in the direction of the force with an acceleration that is directly proportional to the force and inversely proportional to the mass of the object. That is how you tie it in. Now, no matter how you decide to explain or state Newton's law, you need to make sure that whatever variation of how you state it has these two key phrases, because if you do not have these two key phrases, you will not get the 2 marks that is required of you. Okay, so always make sure to have these 2 key phrases as a part of your statement at some point. Make it coherent, make it nice to the ear. Doesn't necessarily need to be nice to the ear, but you get what I mean. Okay. 2.4. Calculate the value of m by applying Newton's second law to each block while they are in motion. Okay, so once again, because we have chosen downwards as positive in the first calculation, we will continue to choose downwards as positive in this question. Okay, so the first thing that you're going to do for this question, because it is looking for the value of m on the second block, okay, or the value of m to each block, okay, we start with F net equals ma. That is always the beginning of our formula. Now we know from our formula that F net for block B, let's start with block B. Okay, for block B, we have already calculated what the net, we have already shown what the net force on block B is. Okay, we've shown that the forces acting on block B are the are the tension and the gravitational force. Thus, you have Fg plus the tension is equals to ma. Now, remember that we have chosen downwards as positive, and if downwards is positive, then that tells us that mg, which is our force due to gravity, minus the tension is equal to ma. Okay? The mass of block B is 7.5. G is 9.8. Okay? Minus T equals 7.5 into 3.88. Okay? This tells you that T is equals to 44.40 newtons. Okay? Moving on to block A. Okay? Now let's start off by drawing a free body diagram for block A while it's in the air. The same as block B. Block A, while it's in motion, has the tension force acting on it as well as the force of gravity. Tension and gravity. So that means for block A, similarly, F net equals ma. Okay. So for block A, we may then choose, we have chosen downwards as positive, right? Since we've already chosen downwards as positive, let's follow the convention that we've been working with and continue in the same vein. Downwards is still positive. So that tells you that mg minus t equals ma. But in this case, we don't know the value of m. Right? So this is going to be 9.8 m minus, now the tension we've already calculated to be 44.40 newtons. So this is going to be 44.40, which is equal to m multiplied by minus 3.88 meters per second. Now, you may be asking yourself, why is the acceleration negative in this case? Remember that we chose down as positive because block A is moving downwards, and it's moving downwards at an acceleration of 3.88 meters per second. But remember, as block B is moving downwards, it's also pulling block A, and block A then starts to move upwards at the same acceleration, but in this case, it's in the opposite direction. Thus meaning our acceleration has to be negative because in this case, upwards is negative, okay? Which is why we have that negative right there. This then tells you that when you do your algebra 9, we can have m into 9.8 plus 3.88 being equals 44.40. And finally, this tells me that m equals 3.25 kilograms. Okay? Wonderful. We're on 2.5. Calculate the maximum height above the ground reached by block A. Okay? So the simplest one for this, we may choose, in this case, we may choose upwards as positive. Let's choose upwards as positive to make things interesting, okay? If we choose upwards as positive, we may start with, okay, so we're looking for the maximum height above the ground reached by block A, okay? And in the same vein as when we were trying to find the acceleration here, we may use the exact same formula to try and determine the change in displacement for block A. So what was our formula? Vf squared is equals to initial velocity squared plus 2 times the acceleration multiplied by the change in displacement, or the change in distance, which is the displacement, sorry. Okay, our final velocity, the final velocity, why is the final velocity 0? Our final velocity in this case will be 0 because remember, for the period of motion, when block B reaches the ground and becomes stationary when block B reaches the ground at a speed of 3.41 meters per second, block A also went up at a speed of 3.41 meters per second. So meaning block B's final speed is block A's initial speed, okay? So Vf final is 0 squared, V initial is 3.41, remember, because we are choosing upwards is positive this time, plus 2 into minus 9.8, because why? That is the gravitational acceleration, okay? Delta y. This tells you that 2 into 9.8 delta y is equals to 3.41 squared. Delta y is equal to 0.59 meters. Okay, now, but then remember that during the motion, block B started off at a height of 1.5 meters, okay, and it went down. That means the maximum height reached by block A should also account for the 1.5 meters that was traveled initially, okay? Therefore, max height will be equals to the 1.5 meters plus the 0.59 meters, which is going to give you 2.09 meters. Now, there's multiple ways in which you could approach this question, as well as the first question. Let's look at the first question first. Let's look at what other ways you could approach 2.1. For 2.1, you could use the approach where you try and find the time before you can find the acceleration, okay? And once you've found the time, you can then use that to find the acceleration, okay? So the first thing that you're going to do is you're going to use delta y is equal V initial plus V final over 2 times delta t, where your delta y is 1.5, your initial is 0, and your final is 3.41. In the case where downwards is positive, our final velocity is positive, okay? Over 2 multiplied by delta t, your delta t will thus be equal to 0.88 seconds. And then you plug this into Vf is equals to Vi plus a delta t, or delta y is equals to Vi delta t plus 1 over 2a delta t squared, okay? Where your Vf is minus 3.41, and here your delta y is minus 1.5, your Vi is 0, and your acceleration, your time is 0.88, and you try to find your acceleration, which is 3.88, okay? Or here your initial velocity is 0 into 0.88 plus 1 over 2a into 0.88 squared. You'll find that your acceleration is equals to 3.88 meters per second square. But since they are looking for the magnitude, you can just write this as 3.88 meters per second squared, since we're just looking for the magnitude. And then for 2.5, for 2.5, you could have started off with Vf is equals to Vi plus 8 delta T, which would have taken you to delta Y is equals to Vi delta T plus 1 over 2A delta T squared, where you have taken upwards as positive or negative. Your third option, you could have started with, this is option 2. This is option 1. Okay. Option 3. Your option 3, you could have started with Vf is equals to Vi plus A delta T, which should have taken you into delta Y equals Vi plus Vf over 2 delta T. Okay, where here you find delta T, which is Vf minus Vi over A, and then you substitute into delta Y to find delta Y. Similarly, you also find delta here. You have to find delta T here and substitute into delta T there to find delta Y. Okay, your fourth option would have been to use conservation of mechanical energy. Okay, so for conservation of mechanical energy, you would have started with mechanical energy at the top is equals to the mechanical energy at the bottom. Okay, which means that the potential energy plus the kinetic energy at the top is equal to the potential energy plus the kinetic energy at the bottom. Okay, this is V final, this is V initial. Okay, so from here we know that the potential energy of block B at the top, sorry, of block A, the potential, we know that the potential energy is given by 9.8. We can just in this case, because we are looking for the height reached by A, we can just divide by M, because all the M's are the same there, to have such that we have GH initial plus 1 over 2 MVI squared is equals to GH final plus 1 over 2 V squared final. Okay, this M shouldn't be there. Right, now from here, G is 9.8. We don't know the height, we don't know the initial height, plus 0, because remember our box was at rest. Okay, remember our box was at rest, which is equals to 9.8 multiplied by 0. Now please excuse me, I have used the wrong subscript. The subscripts here, this is V final and this is V initial. This is final, this is initial. All right, so the initial height of block A was 0 plus 1 over 2, and the initial velocity of block A is still no, the initial velocity of block A is not 0, but rather 3.41 meters per second. Okay, now this will tell you that H is thus 0.59 meters, and then you just put that to max height is equals to 1.5 plus 0.59, which is just 2.09. Okay, And you could also use the non-conservative force formula, where the work done by a non-conservative force is equals to the change in kinetic energy multiplied by the change in potential energy. You could use the work energy theorem. There's a host of other possible ways you could use to solve this equation, but hopefully the four that I've given you so far will suffice, and they make sense enough that when you look at a similar question, it won't be too tough for you to connect the dots. Right, moving on to question 3. Here is our question 3. I'm just gonna move this and put it there. Okay, question 3. Ball A is dropped from rest. Ball A is dropped from rest, which tells you V initial is equals to 0, right? From the top of the building at 15.2 meters high. Okay, after ball A has fallen 3.2 meters, a second ball B is projected vertically upwards from the ground. After a while, the two balls strike the ground at the same time. Okay, 3.1. Define the term free fall. Again, you have two key phrases, and your key phrases are only force and gravitational force. Now, how would you tie this in together? You would tie this in together by saying free fall is motion under the influence of gravitational force only. Or you could say motion, again, you could say free fall is motion in which the only force acting is the gravitational force. Okay? That's how you tie it in. But you need to have these two key phrases. 3.2. 3.2.1. Calculate the time taken for ball A to strike the ground. Okay. The easiest one we could use is delta y is equals to vi delta t plus 1 over 2a delta t squared, because we are looking for the value of t, and we know that the initial velocity of A is 0. So this will just become, let's choose, we are choosing upwards as positive, and because the ball is falling 15 meters, delta y is going to be negative, which is equal to 0 multiplied by delta t plus 1 over 2 into minus 9.8 delta t squared, because remember, downwards is negative. In this case, we've chosen upwards as positive. Okay. After some manipulation, you will find that delta t squared is equal to 2 into 15.2 divided by 9.8. Delta t will thus be equal to 1.76 seconds. Now, this is the easiest way or the quickest way in which you can find the time taken for ball A to strike the ground. You could use a host of other methods where you use Vf squared is equals to Vi squared plus 2a delta y, which would need you to then find Vf first, which you would then plug into either Vf is equals to Vi plus a delta t, or you would then plug whatever you find for Vf into delta y is equals to Vi plus Vf over 2 multiplied by delta t. So you could use a host of multiple different systems. You could use conservation of mechanical energy, which you would use to find the velocity, and then after finding the final velocity, you would plug into one of these equations of motions to find delta t. So when I say this is the easiest, most convenient one, believe me, it is. Moving on to 3.2.2. Uh, 3.2.2. We're required to find the magnitude of the velocity with which ball B was projected from the ground. All right. Now, we know that ball B falls to the ground. Ball B is projected up after ball A has fallen a distance of 3.2 meters. So what we can do first is we can try and find the amount of time it takes for ball A to fall that height or that distance of 3.2 meters, and use that time to find the amount to find the amount of time it would take for ball B to be projected up, and finally find the initial velocity for which ball B was projected up by using the fact that when it reaches maximum height, ball B will have velocity 0. Okay, now let's just go through it so that you can see what I am talking about. The first thing we do is we try to find the amount of time it takes for ball A to fall 3.2 meters. So it's going to be delta y is equal to v initial delta t plus 1 over 2a delta t squared. Okay. Our delta y, we are still choosing upwards as positive. Minus 3.2 is equal to 0, because remember the initial velocity of A is 0 as it was dropped from the height. Okay, is equal to 0 plus 1 over 2 into minus 9.8 delta t squared. After all your algebra, you will find that delta t is equal to 0.81 seconds. Okay, now remember that ball B is projected after ball A has completed this motion, right? So meaning the amount of time that it takes for ball B to reach its peak, okay, to reach its maximum height, is the amount of the two balls strike the ground at the same time. Okay, so it means that ball B was projected up after ball A was released downwards. Okay, so now this means that the entire motion of ball B going up and then coming back down, okay, is equal to the amount of time that it took for ball A to fall from this height, okay, let me use a different color, from this height to the ground. Okay, so let me clear that up. The motion that it takes for ball B to go up and come back down to the ground takes the same amount of time as it takes for ball A to move from this height, which is 15.2 minus 3.2, that's this is 12 meters. 12 meters. It takes the exact amount of time for both these motions to occur. Okay, so that means that the amount of time it takes for ball B to complete its motion is given by delta TB is equal to 1.76 minus 0.81. Remember, because 1.76 is the total time it takes for ball A to travel to the ground. And the answer for that will be 0.95 seconds. Okay, now we know that for our ball, B, the displacement is equal to 0 because our ball leaves the ground and then returns the ground in the amount of time that is 0.95 seconds. Okay, so now what we can do is then use the very same equation of motion to determine the velocity of ball B as it was launched. So we can then say delta y is equals to vi delta t plus 1 over 2a delta t squared, where we know that delta y is 0 because remember it went from the same point right back down, okay, is equal to the initial velocity multiplied by the time, so that's going to be 0.95 v initial plus 1 over 2 into minus 9.8 multiplied by 0.95 squared tells me 0.95 vi is equals to 1 over 2 9.8 0.95 squared. Thus vi is equal to 4.66 meters per second. Now, some of you might want to say this is a bit complicated. Some of you might be thinking this is a bit complicated. Isn't there an easier way for us to do this? Okay. There is a different way that we can approach this question, and a different way that we could approach this question is we could then come and say that the time that it takes for ball B to come from the ground up to its maximum point is half the time it takes for it to complete its motion. Okay, that's okay. So we're gonna thus say delta TB is equal to 1 over 2 times 0.95, which is let me grab my calculator. 1 over 2 of 0.95. That is 0.475. Okay, and we know that the highest point occurs when v final is equals to 0. Okay, so we can thus take v final is equals to v initial, right, plus a delta t. From here we know that v final is 0. We don't know v initial plus minus 9.8 into 4.75. vi is equals, sorry, this is 0.475, and vi will thus be equals 9.8 multiplied 0.475. Hey, look at that, the same answer, 4.66 meters per second. And that is it for question 3.2.2. Dealer's choice, you decide which method you prefer. Would you rather consider the motion, the entirety of the motion for ball B, or would you consider the half motion and make life a little bit easier? Okay. Moving on to question 3.3. Okay. On the same set of axes, on the same system of axes, draw position and time graphs to show the motions of both ball A and ball B from the instant ball A is dropped until the time it reaches the ground. Take the ground as the 0 position. Okay. Clearly indicate the starting time, the initial position, and the time when the ball strikes the ground. Okay, so we'll start with, okay, let's just do the graph. Let's just do the graph. Here is my axis. there. This is 3.3. Okay, there is our axis. Okay, now we're looking for, this is position. Okay, I think there's a better graph I can use for this. Yes, there it is. Okay, we are looking for a position in meters versus time in seconds. Okay, now position versus time graph. We know that ball A is dropped from a position of 15.2 meters. All right, and it reaches the ground after 1.76 seconds. So this will be our graph for A. Now for B we know it is released from ground position, meaning it's released from the 0 position. It's released from ground, which is the 0 position. Okay, up until, okay, it is moved from the 0 position, and it is released after 0.81 seconds. Remember, because 0.81 seconds is the motion, is the amount of time it takes for ball A to fall 3.2 meters. Okay, and then it reaches a peak at some position that we don't know, and finally comes back down right there. So that is our position versus time graph for choosing upwards as positive. Of course, if you choose downwards as positive, the graph would just flip about the x-axis, and that would be the end of that. All right, thank you so much for joining me. I will see you next time.